Hi everyone, here's a quick walkthrough of a question 4 in MyLab on section 8.1. It's modeled after problem 13 in that section in the book. What I had to do here is click on this button to actually get a graph, and this is really just the conceptual graph that I need to do this problem. I'll go ahead and step through all parts, but what we're given is this graph is the distribution of a sampling distributions of means. Sampling distribution of mean is shown, so that's one way I know. Here it tells me sampling distribution. Here on the horizontal axis it's labeled as x bar, which is the mean of some variable x for a given sample size. This picture doesn't show me the sample size, but later in the problem we do take a sample size. So what's going on is you have some underlying population x. We don't know much about it. We're sampling it. We're taking the mean of those samples, of each sample, and we're looking at the distribution of those sample means, and they're telling us that's the picture we get. So the question is, what's the value of mu sub x bar? That's the mean of the sampling distribution. And the central limit theorem will tell us that the mean of the sampling distribution is equal to the mean of the underlying population. In other words, mu sub x bar equals mu sub x, and that's why I put a 500 here, because that's the center of this 500. What's the value of sigma sub x bar? Well, in this case, we're just got to read the standard deviation. Oh, I'm sorry. What I had said is true about the central limit theorem, but I didn't really need to invoke it here. We're just reading it off this normal graph, right? This tells me the x-axis, the horizontal axis is actually x bar. It is a normal curve, and they tell us this, and so the center will be the mean, which is 500, so that's just right there. Similarly, sigma, off of a normal curve, sigma is the distance between the center and each inflection point, which is symmetric, so it doesn't matter if you go right or left. So the distance between 500 and 480 is 20. Similarly, the distance between 500 and 520 is 20, and that's why I put a 20 here. That's the standard deviation of this normal curve. Now, if the sample size is 16, what's likely true about the shape of the population? Well, if sample size gets large, what the central limit theorem says is that as the sample size gets larger, the sampling distribution of means becomes more and more normal. Well, they told us the sampling distribution of means is normal. So in general, that doesn't really, for a large sample size, that doesn't really tell us anything about the underlying population. However, a sample size of size 16 isn't considered large. The general rule of thumb is that above 30, even if you have a pretty skewed underlying population, if you take a sampling distribution of means of size 30 or above, you expect that sampling distribution to be normal. Since this is lower than 30, it's not big enough for the sampling to kick in and create the sampling distribution being normal, but yet we're told the sampling distribution is normal, so it must mean the underlying population was already pretty normal. And that's why the answer should be A. If this sample size was bigger than 30, say it was 50, say it was 60, then the correct answer would have been D. The shape cannot be determined because you can't tell what's going on there because the sampling makes everything look normal in the sampling distribution for a large enough sample size. Okay, part D, get this out of the way, it says if the sample size is 16, what's the standard deviation of the population sample? And what I've done here is put together a quick little algebra problem. So what we know is that the sampling distribution of the standard deviation of the sampling distribution of means, that's sigma sub x bar. Let's see if I can make this bigger. Yeah. Sigma sub x bar is equal to sigma of the underlying population, I should have had a sub x there, divided by the square root of the sample size. So this comes from the central limit theorem. I should have put a little sub x here. I guess I can do that real quick. Just to point out that what we're solving for is sigma sub x. Okay, So I have sigma sub x bar and sigma sub x. And so I wrote this down straight from the central limit theorem. I'm going to plug in the values that we know from this problem. We know that sigma sub x bar was 20. We don't know, and we're asked for, sigma sub x. And we know that n is 16. So when I plug them in, I evaluate the square root of 16, which is 4, multiply both sides by 4, and I can solve for sigma sub x, and it gives me 80. And that's what the correct answer would be. Okay. Keep them coming. If you have any more questions, let me know via Pronto, and I'll make more videos.